Hey everybody, and welcome to this video where we are going to talk about multivariable calculus. And so you've learned how to integrate, you've learned how to differentiate using a single variable, and now we're going to up the ante and use multiple variables. And this is useful when we're thinking about objects or shapes in higher dimensions, or we're even modeling some phenomenon that has many factors or variables or inputs that influence an output of that system. And so when we think about higher dimensions, the integral is very valuable, and it's very difficult to visualize beyond 3 dimensions any shape or object. In fact, I can't do it. Maybe you guys know techniques for really understanding and interpreting and comprehending 4-dimensional, 5-dimensional space, but I am unable to intuit my way through that understanding. In addition, there are many theorems and mathematical applications involved in multivariable calculus that will go beyond the scope of this video, like vector fields, Stokes' theorem, divergence. Like here is an example of divergence where all the vectors are pointing away from a single point, and convergence, curls, and really just a lot of things that deal with linear algebra. We are not going to cover those topics, and we're going to focus on the 2 primary concepts, the 2 central concepts in multivariable calculus, which is the partial derivative or partial differentiation and double integrals, or multiple integrals, but we'll focus on double integrals. So with that, let's jump right into it. Okay, so when we think about multivariable calculus, it's important to understand, like anything in math, the notation for it. And so it's pretty straightforward in that before, when we had a single variable, we would write something like a function of x equals some equation like x plus 4 or something like that. It's very simple. This is a single variable function. A multivariable function would just have an indication using a comma that there is more than one variable input into this function. And so this is a 3-dimensional shape. Let's say x plus y plus some constant. And this is 3 dimensions because f of x, y is an output along a 3rd dimension, right? We have dimension input x, dimension input y, and these give us z, for example, where f of x, y is equal to z. So you commonly will see this as something like this. Something along these lines, where this, let's say this is the x-axis, so this is our input for x. It could be anywhere along this axis. When we have our y-axis, so our input for y could be anywhere along this axis. And then our z, which is equal to f of x, y. And so we're moving up this. And so this is a multivariable function. And this can go on forever, really. You could have any number of variable inputs for a given equation. And so this is an important notation for when we think about multivariable calculus. And so from this point on, we will think about the partial derivative. And you already know how to differentiate, but now we need to be able to differentiate along multiple variables instead of just a single variable. And so that requires us to use a new symbol called the del. And the del looks something like this. Very similar to our other derivative operation sign, but this time it's a little bit more squiggly than the previous single variable operations notation. So this is single, and this is multiple. And now it's an important interpretation of the partial derivative is that it's not different than the single derivative, other than that this is indicating to us that we are dealing with a function that has more than one variable input, and we are holding the other variables constant. That is what this is telling us. We are finding the derivative, the partial derivative of, let's say, we had a function that had f of x, y, z. By finding the partial derivative of this equation, we would be finding the partial derivative with respect to x for f of x, y, z. We are finding it with respect to x. We are keeping y and z constant for the equation x plus y plus z, for example. So y and z would basically go to 0, and we'd find the derivative of x. By differentiating an equation using a partial derivative, we are able to see and analyze how a system's function changes with a small change in a single input, while keeping the other inputs constant. And you can do this for all of the inputs and sum them up and find the total derivative, the total differential. And in this way, we are able to see how a real-world system, because most systems that you will encounter in the real world will have many inputs, not just a single input. And we can see how this, whatever you are studying, behaves, which is valuable if you're a scientist or an analyst or in any sort of position that relies on predictive prowess and modeling. So now that we understand the notation a bit, let's move on and actually do an example using the partial derivative. So let us imagine that our equation, our example for this is f of xy equals x to the third power y. And I'm going to keep this very simple just because I don't want this video to go too long, and increased complexity will make the video too long. And so f of xy equals x to the third y, and we want to find the partial derivative of this. So we want to find the partial derivative with respect to x of the function f. And this equation is x to the third y. And so the partial derivative of this, we would find the derivative with respect to x. So we do our derivative properties on x to the third. So we get 3x squared, and y is a constant, and because it's being multiplied, we can just leave it as is. And here is our partial derivative. We can see now that this is an equation representing a small change in x if we keep y constant, and how that would impact our function's output. And we could take the partial derivative with respect to y as well, and then we would get the total differential of x to the third y, and we would get x to the third as our equation, because the derivative of y is 1. And so x to the third plus 3x squared y, these are the two equations that give us our total differential. And I don't know if you guys noticed, but this is actually written differently, and that was a mistake of mine. This would actually not be here. This f would not be here, and it would be written more like this. We would take the partial derivative of f equals the partial derivative with respect to x of x third to the y. And same thing down here, it would be partial derivative of f over the partial derivative with respect to y equals the partial derivative of our equation x third to the y, which is equal to x to the third. And so that's just a little nuance and a little mistake I made that I caught. And then from here we could even take the second partial derivative of each of these partial derivatives. And there are some unique and interesting properties associated with second partial derivatives, in that you get a sort of symmetry that takes place where no matter what second partial derivative you take, it will equal the other second partial derivative. But we will not go through that here, and we will save that for another time, because we need to move into integration. Okay, so now that we know how to differentiate, let's move on to integration. And if you recall, when performing integration of a single variable f of x, we had a notation that looks something like this. And what this is telling us is we are finding the limit. This integral sign tells us we are finding the limit of the Riemann sums, which were those rectangles, if we want to visualize it, between the function's outputs from, let's say, A to B. It'd be this area here. These Riemann sums would be an infinite number of rectangles as the width of those rectangles reaches 0, which is represented by this dx. And we were doing that from A to B for the function f of x. And so this is how we would do it for a single variable. But now we have multiple variables. And so this requires us to use the double integral of a function f of xy dx dy. And this would be our notation for finding the volume, whereas before this was the area. But now we need the volume because we are working and operating in 3 dimensions. And so we have this double integral notation. And this could be from, as we will see, it will be from 0 to B and 0 to A is how I have done it. And we will use a visualization for this because I think that is the best approach when trying to get an intuitive understanding of the double integral, which is the purpose of this video. And so imagine we have our x, y, z. This is z, which is equal to f of xy, right? We have our y-axis, and we have our x-axis. So this is our axis. This is our graph, our 3-dimensional graph. And let's make this explicit. Z equals f of x, y. And so when we are integrating, we are really just keeping when we're using a double integral and we are integrating, we have to keep one of these variables constant. So remember we had our plane, we are building that plane again, but we were building our 2-dimensional plane in a 3-dimensional field, a 3-dimensional space. And so let's say we have our point here along the y-axis. We will keep, let's use a different color, along the y-axis. And we are going to integrate with respect to x first. That's what is indicated by this first integral in dx. Is here we will do an integration from 0 to b of f of xy dx first. And then the second integral will be performed on the product of that, the output of that integration. We will integrate that, if that makes sense. So, we are keeping y constant and we are moving along the x-axis. So at this point, x is equal to 0, which is indicated by this right here. X equals 0, x equals 0. And so we are moving along our x-axis right here. And so we can draw our plane. Boom, it looks something like this. A nice rectangle. And so we have another point right here. This point is when x equals b, which is right here. Let's use another color. X equals b is right here. And x equals b is right here. So remember, we are integrating from x equals b. And so we have our plane here. We can shade this in so it's not so confusing. We have our plane. And we are intersecting 3-dimensional space. So imagine f of xy was a prism that ran across just like this. Just like this. We have our prism. And so, we've cut a piece of this prism, and that is what is indicated by this first integral. And so we would find the antiderivative of this function f of xy, which output this prism for us. And obviously there's no expression here, it's just f of xy, so we won't be actually performing the antiderivative. But let's say we got our answer. We found the antiderivative of this. And so we now find from 0 to a the product, this blue product. Our first integral. Integral 1 dy. Let's put dy. Let's put it in white. So now we need to find the integral of dy. And in order to do that, we now need to move along the y-axis. So now we are keeping x constant. Let's say right here. Right here, y is equal to 0. And we are going across, let's say we can see through this plane. Boom. Straight up as well. Right here to right here to right here. And let's shade this in. And if you try to visualize this, you can see that this green plane gives us depth, so we can have our volume at y equals 0, and then this point right here, which is y. Y is equal to a. And our a is right here. Our a is right here. And our 0 is right here. Our 0. 0, 0. So we are integrating this plane from 0 to a. And we are performing this integral operation on the product of the f of xy dx from 0 to b integration. And remember, we are doing it from 0 to b and 0 to a, so these are definite integrals, and definite integrals rely on the fundamental theorem of calculus, which I did in a previous video. So I've already done this in a previous video if you want to go through how we actually integrate a function and find the antiderivative. But the purpose of this video was to see how a double integral worked, and we can see how we are finding the volume as a slight change in dy. So we're moving along the dy axis, and before that we were moving along the dx axis, along the x-axis. And so now we have depth and volume of this blue prism here. And that's what this double integral tells us. There are also an option to do triple integrals, which deal with mass and density, but I won't go through that here. And with that, I think we can wrap up this video, and we'll see you in the next one.